spiral similarities, and inversions. So we
Opo.
haven't done that. And then, ano ba, meron pang number theory. We haven't done number theory. We also haven't done combinatorics.
Oh,
So,
no.
di ba? Kaya
We
madami mga pwedeng pag-usapan. But I was thinking, gusto ko magpahinga sa sa geometric transformation. So let's do a little bit of vectors. Now, a vector is a quantity that has, oh, wait, hindi pa pala connected. So I know you've already seen vectors from your maybe physics classes. And so, all right. Okay, so the pen is activated. So a vector is an object which has length and direction. So typically for a high school student, the term vector is first introduced when trying to make a distinction between, for example, distance covered and displacement. So let's say you have a person that's moving along a straight path, and the distance would be, let's say, how many meters did this person walk? But when you talk about how many meters, there are many ways that the travel could have been done, and the travel could have been done through different directions. And so there's a need to capture not just magnitudes, but also directions. And so a vector is a quantity that has both magnitude and, when I say magnitude, it's the same as length, and it also has direction. Um, Two other quantities that are encountered in physics, which illustrate the distinction between a vector and, so on one side you have vectors and the other is a scalar. So when you think of scalars, you just think of numbers. So um, velocity versus speed. So when an object is moving, that object's speed quantifies the rate at which this object is moving. But velocity says something more rather than just the speed. The velocity of a moving object also captures the direction in which the object is moving. All right. But mathematically, when we think of a vector, we can think of it as a segment with an arrowhead. So we can think of a vector like that as a geometric object. So let's say we have a point A, and then here is that's another point B. So this is the vector denoted by A, B with that kind of arrowhead. Okay, I know we're using the same symbol for array, but the thing about array is that it goes infinitely in one direction. On our part, the vector AB starts at A and ends at B.
yung ano ko
So
po,
it's a
yung
segment with a direction.
opo.
Yes, go ahead.
Yung ano po, yung proposition ko po is to make yung vector, dalawa pong ganun sa arrow niya.
Sa taas to distinguish it from array.
Opo.
Okay, that works, but of course, this is how you write vectors when you're using a pen. In textbooks, they just present vectors, well, sometimes as characters in boldface.
Opo.
All right. The vector AB and the vector BA are different. Even though they are connecting the two same points, B and A, but vector BA denotes travel from point B going to point A. Now, these two vectors have the same length, but different directions. If it's just an issue about the segment connecting A and B, there's only one segment. But there are two vectors to talk about between A and B. It's the same length, but different directions. Right now, I am teaching math majors their third calculus course in a sequence, and we're doing lots of things with vectors. Vectors are very useful, as they've seen, in analyzing the geometry of three-dimensional space. For example, if you look at the equation y equals mx plus b, or you
Ano
could
po?
replace
Directional field?
mga ganun. Yeah. But we're not even there yet. So the comparison that I wish to make is, for example, we have 2 points on the plane, A with coordinates 7, 3, and B with coordinates 10, 5. There is a unique line passing through A and B. And with sufficient knowledge of algebra, it is possible to come up with the equation of the line through points A and B given their coordinates, because given these two coordinates, we can find the slope. And then you could use either point A or point B to complete the equation of the line. Now, the slope in this case is a number, and it captures whether the line is increasing or decreasing. But of course, if the slope is zero, then the line is neither increasing nor decreasing, because it's just of a constant value as the graph of a linear function. Now, what if the points A and B are in three-dimensional space, meaning A has three coordinates 7, 3, -4, and then B has coordinates 10, 5, 6.
Saka kung ano
I
po to,
am,
kung in 4 dimensions kaya po, will it still be explained by vectors?
but have you encountered how to describe how to come up with equations for line AB in three-dimensional space? I wanted to know where we are right now as far as you're concerned.
Hindi ko po alam.
Is it? All right. Okay. So with in the plane in R2, so the equation is gonna have the form y equals mx plus b. For R3, what's gonna
Quadratic kaya
happen
po.
is that quadratic, hindi
Ah,
quadratic, but well, it turns out that there's going to be a system of three equations, but then the derivation is based on a knowledge of vectors. Now, in R4, in four-dimensional space, the way I see it is that actually, yes, we can still describe the equation of a line in four-dimensional space or in five-dimensional space using vectors still. Okay, so vectors are very much well suited to addressing problems in three-dimensional space. So ito, finding an equation pangalan for a line, it's not that straightforward na because the points have three coordinates. What more when you want to describe the trajectory of a projectile in three-dimensional space, and you want to perform a quantitative analysis, so you want to determine such things as the velocity of a moving object in three-dimensional space. So one of the main tools that make all of these possible are vectors. Okay, so all right. So while vectors were devised initially to capture length and magnitude, there is an exception though, which is the zero vector. The zero vector has no length. Actually, its length is zero. And actually, the zero vector, imagine starting from A and then you never left. Your destination is also the same point A.
how is that a vector po?
How is that a vector? Well, if you think of a vector as kasi just something that captures length and direction, hindi siya papasok sa what we think of as vectors. All right? Pero kasi when we try to come up with a mathematical system, parang gagawa natin ng mga rules and operations ng mga vectors so that we are able to add vectors just like numbers, and we're able to subtract vectors. And later on, we're going to talk about the multiplication of vectors. We are going to see that there is a need to define a vector that corresponds to the number zero for real numbers. Now, what's so special about the number zero? It's the additive identity. Given any number, if you add zero to it, the result is still the same. So 0 does not change the number that it's added to. And so likewise for vectors, we actually need a vector which when added to any other vector does not change the vector that it
Ah,
was added to. So we need
simply
something that,
fulfill it po, that
ano
role.
yan? What's
Simply,
that?
simply to fulfill the role po of the additive
Yeah, additive identity. So parang we need a placeholder for a vector that denotes no change in location. Also, another place where 0 enters the discussion in the realm of real numbers is 0. You know how 7 and then plus -7, that's equal to 0. So parang 0 is what you get when you combine uh, two numbers which are negatives of each other. So if you look at this figure, you have vector AB and you also have vector BA. Now, the idea when you add two vectors is that, for example, you start with vector AB, you start at A and you end up at B. Adding vector BA means continuing the story. This time you're traveling from B and going to A. But then if you take those two vectors, what that does is you started originally from A, but at the end of it all, you end up at A. So there is no change of location. And so there is a vector that describes all of that, and that's the 0 vector.
Tsaka ano po pala, inisip ko po, is it technically undefined kung if there was no zero vector?
What will be undefined?
The addition po of negating vectors.
Yeah. So para mangyari, you wouldn't be able to add vector AB and vector BA. So there has to be a sum, and in that case, their sum would be the 0 vector.
Opo.
Okay, so in the plane R2, let's say you have these 2 points, 2, 1, and then 5, 3. These are A and B. Now, I'm drawing here the vector AB. Okay. However, if I start from a different point, C, which is here at 6, 0, and then another point, 9, 2, D, 9, 2, and I draw the vector from C to D. Well, okay, that is a different orange segment. But if you compare the two vectors AB and CD, can you tell me, without necessarily finding the length, do they have the same length, these two vectors?
Opo.
And do they have the same direction?
Probably po.
For example, you have two different people, one standing at point A and one standing at point C, and you direct that person at A to look in the direction of B, and that person at C to look in the direction of D. So from where they're standing, and as they're looking towards the destination, do you think the way they position themselves, halimbawa kasi, if I'm gonna look in ahead of me, I'm gonna stand this way. But if I'm gonna look to my left, for example, I'm gonna look this way. So I don't know if you're looking at me, but here's me looking to my left. Now, if you direct those two persons at A and C to look at B and D respectively, are they facing the same direction?
Opo.
Yes, but just to be sure that we are on the same page, why are they? How do you know they're looking at the same direction?
Hmm. Maybe you could base it po on parang coordinate axis nga po. And then make sure the lines they're looking at is parallel.
Mm-hmm. So okay, ganito na lang. Are the two orange vectors parallel?
Opo.
Yeah, you could see that they have the same slope. Also observe that I've drawn these two pairs of blue segments so that we're able to complete our right triangle. And horizontally, we are from A to B, we're traveling horizontally a distance of 3 units and vertically 2 units. And from C to D horizontally, that's also 3 units and vertically 2 units. So the slope for both is 2/3. And so if we think of a vector as something that captures length and direction, because these two vectors have the same length and they have the same direction, then they must be the same vector. AB and CD are the same vector since they have the same length and direction.
Wait lang po. Papatayin ko lang po yung
May papatayin ka? Alright. Sige.
Okay na po.
Alright. Okay, napatay mo na nung papatayin mo. Wait. All right. So they have the same length and they have the same direction. So the thing is, as far as vectors are concerned, the location is irrelevant. Okay. The location is irrelevant. So in other words, you can translate a vector and it doesn't change the fact that it is essentially still the same vector. All right. So for the vector that we have drawn, what we need to do is therefore come up with a way of coming up with a notation that is able to describe the two vectors. And well, we see that horizontally we traveled 3 units, and vertically we traveled 2 units up. Then 3 and 2 are what we're going to refer to as the components of the vector AB, which is also the vector CD. So AB.
Yung ano na po, yung how much X na, how much X travel and how much Y travel.
Yeah, AB equals CD, and they each have 3, 2. So one way to think about how we can come up with the components is that let's take the point of view of A. For A, the coordinates of A rather are 2 and 1, and for B, the coordinates are 5 and 3. If you take the difference of the x coordinates from A going to B, so that would be 5 minus 2, that would be the first component, 5 minus 2. And if you take the difference of the y coordinates from 1 going to 3, that's going to be 3 minus 1, and that is what accounts for the second component, 2. All right, so that's how you write down a vector in terms of its components. So for example, if vector v is the vector -7, 5, and this is the vector pq, where p is the point with coordinates ano ba, negative confusing naman parehong -7. Let's make this -3, comma, -8. Then find the coordinates of Q. Okay. So, well, all that means is that if Q has coordinates A, B, then that means the component -7 is the difference of the first coordinates. So A minus -3. I see that this is probably something that you can do mentally. All right. And then 5 is the difference, B minus -8. So from this we get A equals -10 and B is -3. So that means Q has coordinates -10, comma, -3. All right. Now, let's say I'm trying to move this. Okay. If we draw vector V with components AB so that it starts at the origin and ends at P, then P has what coordinates do you think?
BA. AEB.
Yeah, all right. So ito nung origin O, and this is the point P, and we're looking for what the coordinates should be. We realize that the coordinates of P should be A, B as well. All right. So A, B. Okay, and you can verify that those are the right coordinates of P because then vector V will be A minus 0, which is A, and then B minus 0, which is B. But strictly speaking, all right, if you have the vector whose components are given A, B, then the terminal point P will only have AB as coordinates if it is drawn starting from the origin. Naturally, if you were to draw the same vector but starting at a different point, then the coordinates of the terminal point will not be AB because it will also be affected by the coordinates of the initial point. Okay, so in this case, the zero vector is denoted by 0 with an arrowhead, and the components are 0, 0. Okay, and we can imagine that if we were to draw this starting from the origin, so 0, 0, but then the destination will be 0, 0 as well. So you never left. Okay.
Wala talaga.
Oo, wala talagang ano. So, parang no net effect is, well, starting point and the destination are the same. In R3, okay, if P given the coordinates A, and let's say the coordinates are M and P, and the point B with coordinates Q, R, S, then vector AB is going to be a vector whose components are derived similarly. Q minus M, R minus N, and S minus P. In R4, or higher dimensional space, where points have not just, wait, hold on. I may be making certain assumptions here. Have you encountered three-dimensional space where you have your x-axis, y-axis, and z-axis before? Have you encountered that, Joshua?
Opo.
Yes or no?
Yes po.
All right, all right. So points with three coordinates is not totally alien to you. So you've seen this before. All right, so the vector AB would have components based on the coordinates of A and B, and then defined similarly. And then likewise, if we were to look at vector V with components A, B, C, and draw the vector so that it starts at the origin. So let's say that's vector v with components A, B, C. But because it was drawn starting from the origin, then that would mean its terminal point has coordinates A, B, C as well. Okay. Um, Vectors in R4 in four-dimensional space, connecting points, each having four coordinates. This can be discussed in an abstract manner, although hindi na natin siya kayang i-drawing ng four-dimensional space. Also, five-dimensional space or higher dimensional space. All right, kasi if we want to draw points in R4, di ba, kailangan natin x-axis, y-axis, z-axis, and also w-axis. And now these four axes must all be concurrent, passing through the same point that we're going to label the origin. But any two of them must be perpendicular. Have you thought about whether that's possible, Joshua? A collection of four lines, all concurrent, meaning passing to the same point, such that any two of them are perpendicular.
Mm. It's beyond our it's beyond our physical.
Yes, yes, it's beyond our perception because we are three-dimensional beings. So we can only talk about R4, R5, and higher dimensional spaces in abstract ways, but not really concretely in a way that we can visualize because uh, our vision is three-dimensional. All right. Um, Vectors have lengths. So let's say vector V has components A and B. What is the length of this vector? What do you think? The length is denoted by putting the vector V between two vertical bars. Strictly speaking, this is not absolute value because V is not a number. But just the same, it acts like absolute value. Okay, after all, in the real number line, here is the origin, and here is -7. We say that the absolute value of -7 is equal to 7 because if you look at this point corresponding to -7 and measure its distance from the origin, that distance is 7 units. All right, so the absolute value of a real number represents how far it is from the origin. Now, for vectors, when we talk about the length of a vector, what we are measuring is how far the terminal point is away from the origin if this vector is drawn starting from the origin.
So, ganun din po sa complex numbers.
Oh, yeah. Okay. So so the modules of a complex number. Well, for this vector, its length is really nothing else but the distance between 0, 0, and AB. So by the distance formula, that's simply going to be the square root of the sum of the squares of A and B. What about in three-dimensional space? So our vectors have three components. The length is going to be very similar, A squared plus B squared plus C squared.
So, ano po the Pythagorean theorem of three dimensions?
Yeah, the distance formula, actually, yeah, it's pero ganito kasi. When you talk about a triangle is actually a plane figure. Kasi di ba, given any 3 points which are distinct and not parallel, there is exactly one plane through those 3 points. So the coordinates may just be, well, the vertices may just have 3 coordinates, but a triangle is still a plane figure. And so it's actually still the same Pythagorean theorem. What changes though is how you find distances in terms of the coordinates. This time that points have 3 coordinates each. Have you ever encountered the distance formula in three-dimensional space?
Hindi ko po alam bakit po ganun.
Okay, so let's talk about that. Okay, so distance formula in R3. Hold on. I'm gonna ask someone to bring water up to me here. All right, so let's say we're given the following 2 points: A with coordinates hang up, P, Q, R, and then B with coordinates S, T, U. Okay. Um, mm, okay, maybe I don't need the X, Y, and Z axes from pagulo lang. Let me draw a shoebox instead. Pero sige, let me draw. Okay. Nung x-axis is that's the x-axis. This is the z-axis, and then the y-axis is here. Okay, y-axis. Then let me move A. Okay, A has coordinates P, Q, R. Okay, so if it helps, all right, and then we are interested in the length of the segment connecting A and B. The length of that segment is the distance between those 2 points. Let me introduce some auxiliary points here. Let me call this point C. Now, C is directly below B. And if you remember what the three coordinates represent, the x-coordinate represents how far you travel along the x-axis, the y-coordinate along the y-axis, and the z-coordinate along the z-axis. Now, traveling from C to B is vertical, so that is travel along the z-axis, which means that from C to B, you're not traveling in the direction of x or y, so that means C shares the same first 2 coordinates as point B, which are S and T. Now, on the other hand, C is at the same altitude as point A, whose Z coordinate is R. Therefore, C also has last coordinate equal to R. So now, if you look at BC, how long is segment BC?
U minus
U minus
U minus V po. Ay, R pala.
R. Okay, U minus R. All right. Well, U minus R because U is above point C. But well,
Ano
the
na
situation.
naalala ko po ulit eh. Dati po na ano na po to, this was already na ano ko po sa yung ano tawag dun, sa FCC po yung ano po yung close packing ng spheres po. Ianin yung skew distance no, from both corners po. Yung ano po yung sa baba po ng triangle. That is already the square root of something squared to something squared.
All right.
Dinagdagan pa po yung isa.
Okay. So, are you referring to AC?
Opo.
All right. Okay. So ganito. Kasi AC is the hypotenuse of this green triangle, and we already know BC. So that means we only need to figure out the length of AC, and we can use the Pythagorean theorem to determine AB. So the distance BC, I wrote it as U minus R in general because what if point B was actually below C? So mas malaki pala nung R compared to U. But at any rate, the absolute value of U minus R would be the distance, and it's a non-negative quantity. All right, now as for AC, let's introduce another point, point D. Well, for coordinates, let's use the regular blue. Okay. All right, D. Just like A and C, same Z coordinate R because they are all at the same altitude. Now, from A to D, that's travel along the y-axis. So it's a change of y coordinate from Q going to, what's the y coordinate of point dog? What do you think?
Teach.
Yeah, teach. All right. But on the other hand, what is the x coordinate of point dog?
P.
P. All right. And then observe that A, D, the only thing that changed is the y coordinate. So because that's travel along the y-axis, so that distance, that length is absolute value of t minus q. And from D going to C, what changed is the x coordinate between P and S. So CD, that the length of that segment is the absolute value of P minus, let me write it down as S minus P. Para lang uniform dun sa pagsulat natin mamaya. All right. So observe that from right triangle ADC, we see that AC squared is equal to T minus Q squared plus S minus P squared. And then in right triangle ABC, AB squared is equal to, well, it's AC squared plus BC squared. But AC squared is what we actually wrote above. S minus P squared plus T minus Q squared. And then finally, BC squared is U minus R squared. In other words, AB is the square root of S minus P squared plus T minus Q squared plus U minus R squared. And then if you compare that with the usual distance formula in two-dimensional space, we realize, hey, we are in fact doing the same thing. We are taking the corresponding coordinates and then subtracting them and then squaring and then adding and then taking the square root. It's just that this time, because there is a third coordinate, well, we have to consider a third term, but we're doing exactly the same thing. And so even though we cannot visualize higher dimensional spaces, we can define abstractly distances in Rn. If the coordinates of A are A1, A2, all the way to A sub n, and the coordinates of B are B1, B2, all the way to B sub n, then the length of segment AB is the following. You take B sub I minus A sub I squared, and then add as I runs from 1 to n, and then take the square root. You are familiar with sigma notation, right? Summation notation. I ask because it's something that I realize I haven't been using very often. All right. So I run from 1 to n, b sub I minus a sub I squared. And so therefore, in Rn, if the vector v has components v1, v2, onwards to v sub n, then the length of vector v is v1 squared plus v2 squared plus dot 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 plus v sub n squared, and then we take the square root. What is the only vector whose length is 0?
Zero vector po.
The 0 vector. All right, so you see that vector v has length 0 if and only if v is the 0 vector. So as soon as one of the components is non-zero, then that guarantees that the vector is going to have a strictly positive length. All right. This is formula is actually also what leads to the equation of a sphere. All right, because if you consider the collection of all points x, y, z having the same distance are positive from a fixed point C with coordinates P, Q, R is the following. It's going to be a sphere, right? On the plane, given a fixed point, if you try to think of what points are equidistant from this particular fixed point, the only thing they are able to generate is a circle, and that's because the context is a plane. But if the environment is three-dimensional space, then you can consider much more points, and what you get to generate is a sphere. Now, the equation of a surface or a curve is an equation which describes what the coordinates must satisfy to belong to this surface or this curve. And what we see here is that, well, if XYZ has distance r from PQR, then that means, according to the distance formula, x minus p squared plus y minus q squared plus z minus r quantity squared. Oh, hold on, sorry. It is rather unfortunate that I used r for the radius and the fixed point C has r as one of its coordinates. Let me replace r by s. So z minus s quantity squared square root is equal to r. Example. I'm just taking this opportunity to explore the distance formula. You may have noticed that we haven't been, well, this example that doesn't have vectors. But anyway, find the distance between the spheres x squared plus y squared plus z squared equals 4, and x squared plus y squared plus z squared equals 4x plus 4y plus 4z minus 11. Okay, first off, we're talking about the distance, not between 2 points, but between two spheres. All right. If we're talking about two different points, then we just talked about how to find the distance because we can use the distance formula. But what if we're looking at two objects, each of which consists of infinitely many points, and then we're trying to find the distance between them? So first, what do we mean by distance? The distance would be, well, the shortest distance you could get out of choosing 2 points from each collection. Okay, another way is, so let's say you're given two circles. So the distance between them would be, well, you think of all the possible pairings of points that you could come up with, and then what are the distances between those 2 points, and then after taking note of that, what is the minimum among all those different distances? But of course, it's also easier to just think of it as the distance between the two closest points. All right. Well, the first equation is a sphere with center 0, 0, 0, whose radius is 2. And for the second sphere, what do we need to do to figure out its center and radius? We complete the fill in the blank. We complete the pentagon, we complete the triangle, or we complete the rhombus.
We complete the hexagonal tetragon.
Sure, sure. All right. I say okay.
The tetraangle po.
I set the x squared minus 4x plus y squared minus 4y plus z squared minus 4z, and then it's negative 11 on the right side. To complete the square, we have to add 4, 4, 4, which means we have to add 12. So we got x minus 2 squared plus y minus 2 squared plus z minus 2 squared equals 1. So what we have is a sphere whose center is 2, 2, 2, and whose radius is 1. To find the distance between these two spheres, do we need to identify what the two closest points are from the first sphere and from the second sphere? Is that necessary, or can you think of something here?
Lang po, baka kailangan po. At kasi yung center 0, 0, 0, o isa naman center 2, 2, 2.
If it helps, instead of drawing spheres, let's draw two circles.
Parang yung ano na po yung sa great circles.
And this is what we're interested in. How are the two closest points, the ones in orange, related to the centers of the two spheres?
The ano po is the distance from the centers minus the radius.
Yeah, kasi those two closest points happen to be collinear with the centers. And well, we know the centers, right? They are 0. The centers are in green, 0, 0, 0, and 2, 2, 2. So the distance between the centers is, what's the distance?
2 plus, wait, yes.
2 minus 0 squared, 2 squared, plus 2 minus 0 squared, 2 squared.
Yung three-dimensional na.
Oh, so ano to tatlo sila. So what we get is 2 square root of 3. And the rate
po. Yung ano po, diba sa close packing? 2 square root of 3 po yung ganun din.
oh may this time may factor na square root of 3 na, no? Hindi lang basta 2. All right. The radii, on the other hand, are what's the radius? 2 and then 1. So the distance between the spheres is
2 square root of 3 minus 3.
yeah. All right.
Oh.
How do you know the two spheres don't overlap?
Because you can calculate you are sure po that the 2 2 2 there wait. Yes, ganun po, by using observation. The distance between the centers is that. And then since 2 square root of 3 is greater than 3.
Yun. Actually, that's it. 2 square root of 3 is greater than 3. Okay, otherwise, if the two spheres overlap, this difference would have been negative. All right. So this is formula in 3 dimensions, and then we've been talking about vectors. And now that we have the distance formula, we used it to come up with a formula for the length of a vector in any higher dimensional space. All right. Now vectors, just like numbers, can can be subject to certain operations. We start with vector addition.
Is it true po na yung mga ano po some of the properties of vectors, if they don't hold true, does that mean for it's no longer a vector?
Ano yun? Well, if some properties do not, what's that?
If something appears to be a vector point, it's magnitude and direction. But if it does not fulfill all of the something, I don't know. So,
Ang laban yung anong something na hindi fulfill.
If it doesn't fulfill something po, parang a property of vectors. Does that mean it's no longer a vector, even if it has magnitude and direction?
Well, you know what? For me, this sounds highly hypothetical. All right. My initial response would be, well, if there are some properties of vectors that are not satisfied, then it's not a vector, because if it's a vector, then it must satisfy the properties of a vector. Right? So in that case, there seems to be something more going on with this hypothetically magical object.
Opo. Hindi kaya yung ano po, yung mga, baka siguro po yung mga, hindi ko alam. Baka siguro, there are things siguro po na ganun. May tawag kaya po sa mga ganun.
Something which
has magnitude and direction but does not fulfill all of the requirements to be a vector.
Actually, because to be honest, I can't think of anything right now. Quantity or a concept or an object which has magnitude or direction. I can't think of anything right now, kasi so it's all hypothetical to me at this point. If you can think of something, though, let me know. Mas malinaw. So, as far as vector addition is concerned, madaling i-define na, just add the components. All right, but I want to start from this definition, okay, of what it means to add two vectors. So if U and V are vectors position, so the initial point of V is at the terminal point of U, then the sum U plus V is the vector from the initial point of U to the terminal point of V. Okay, going from mathematical, U and V. Kaso nga lang, since vectors, I want to put an arrowhead on top of that. Paano ba yun? Insert math or insert equation. Ayan. Di ba gumamit ng vectors recently? Symbols, and structures. Ito, accents. Ayan. And then in the future, I'll just copy paste. All right, yeah. All right, yeah. If U and V are vectors positions, so the initial point of V is at the terminal point of U, then the sum U plus V is a vector from the initial point of U to the terminal point of V. So let me illustrate this for vectors with 2 dimensions. So let's say we are given the following. Orange vector U with components A, B. And then green vector V with components C, D. So, definition dito, let me use let's draw vector A, starting from the origin. All right, so this is vector U. But if we're starting from the origin, then given the components of U, which are AB, then that means this point here has coordinates AB. Okay, now the definition talks about putting the initial point of V at the terminal point of U. Okay, so this is vector V. Now, what is the terminal point of V then? Well, the difference of the corresponding coordinates between this terminal point and the initial point AB of vector V should be the components CD. So therefore, this point has coordinates A plus C, B plus D. And the definition says the sum U plus V is the vector from the initial point of U, which is here the origin, to the terminal point of V. So this is the vector U plus V. And because we see that when we drew it starting from the origin 0, 0, it ended up at the point with coordinates A plus C, B plus D, then that means these two sums are what's going to make the components of U plus V. A plus C, comma, B plus D. And so what you see here is that, well, because vector U has components AB, and V has components C, D, then the sum is A plus C, B plus D. So what we get out of this is that to add two vectors, all we need to do is add the corresponding components. But also at the same time, we get this interpretation, which is that if you think of a point that's traveling in the direction of U, and then it continues its travel in the direction of V. Now, when you take note of where it really started, right from the very start, and where it eventually landed from the starting point to the final endpoint, that is, well, when you connect them by a vector, that's the sum of the two vectors U and V. So when you add two vectors, basically what we're doing is we're trying to think of where do these two vectors bring us, given how long they are, given their magnitudes, and also taking into account what their directions are. Now, this illustration is for vectors in R2. It is the same story for vectors in space in R3. Okay, let's add scalar multiplication, and then very quickly afterwards, we can talk about vector subtraction. So what is scalar multiplication?
Dot product po.
Hindi pa, hindi pa. Okay, when you take the dot product, it's between two vectors. Scalar multiplication is between a vector and a scalar. But Joshua, you've encountered these operations before, right?
Opo.
Okay, so sige, anyway, if dadaan ko lang. Actually, hindi ko na nga-define kasi parang halos wala na namang ano interpretation. So, sulat ko na lang na ng scalar multiplication. C is, okay, assuming I can figure out the correct spelling of multiplication. So say C is a real number and V is a vector. So two cases, if C is positive, then CV is the vector in the direction of V, okay, whose length is C times the length of V. And then on the other hand, if C is negative, then CV is going to be the vector in the opposite direction. Of vector V, whose length is the absolute value of C times the length of vector V. All right, kasi if C is negative, for example, -2, we cannot multiply the length of V by -2 because then that's going to be a negative number, and this cannot be the length of any vector if this is a negative number. All right, so and then if C is 0, then this is going to be a vector whose length is 0. So therefore, this must be no other than the 0 vector. All right, so for example, if this is the vector u, then the vector, oops, was that same direction? So this should be vector 2u, and then a vector -u would be, well, -1 times vector u. So it has 1 times the length, but opposite direction. And then as for -1/2 u, it's ganyan, -1/2 vector u. So because it's negative scalar, -1/2, it points in the opposite direction as u, but half the length. All right. So In terms of components, let's say there are two components, A, B, and then I think I used violet for the x-axis and y-axis. Again, this illustration is for two-dimensional vectors, but it works as well for, let's say, three-dimensional vectors. And say this is the vector u with those components. And for easy for ease of following the argument, here's assuming this points in the first quadrant when drawn starting from the origin. So that means A and B are both positive. So the right triangle formed here has those dimensions A and B. Now, if we look at the vector twice u, 2u, then what we get to form is a right triangle that's similar to the green triangle, but then the hypotenuse is twice as long, which means the ratio of similitude is 2, which means the dimensions are double the previous dimensions of A and B, and so therefore the base is going to be 2A, and the height is going to be 2B, which means that this point has coordinates 2A, 2B, which means 2U, when we think of its components, they're going to be twice A, comma, twice B. So that means 2 times the vector with components AB is the vector with components 2A and 2B. And so what this is telling us is that in general, if a vector u has components u1, u2, all the way to un, then the vector cu is the vector whose components are cu1, cu2, onwards to cun. So scalar multiplication is something that we do by component. Okay, now what about subtraction? Vector A minus vector B is defined as A plus the vector negative B. So A added to the vector in the opposite direction of vector B. And because addition is done component-wise and scalar multiplication is done component-wise, because when you look at negative b, we simply think of that as the scalar -1 multiplied to vector b. Then we see that if A has components a1 onwards to an, and B has components b1 onwards to b sub n, then the vector A minus B is simply A1 minus B1 onwards to A sub n minus B sub n. So you just do it by components. But what is fun to look at is the geometric interpretation of subtraction. Okay. Geometric interpretation of subtraction. Okay. So let's say we have the following two vectors drawn from, let's draw them from the same starting point. So let's say this is vector A, and this in green is vector B. And let's think of where is A minus B going to appear here? Okay, so we observe that, hey, A minus B, if we add that to vector B, the result is going to be vector A. And so, well, remember the interpretation of vector addition earlier? if you add two vectors, you think of traveling continuously along one vector and then continue it by traveling along the second vector, and say the second vector is B and then the net result is A. So that means A minus B is what you need to do after traveling along vector B. Now the green vector B is drawn there. All right. And then let's say you started here and then now you're here. And now we are trying to think of a vector so that in the end, the net result would be travel along vector A, which ends here. But then that means, well, if we want to end there, and here is where we are now, then this is what we need to add. This is what we need to follow to continue the journey, which means this must be vector A minus B. So that is vector A minus B.
Opo.
Okay, so here are some properties of vector addition. So vector addition is commutative. All right. It's also associative. Vector addition is commutative. And it's also associative. Well, actually, instead of writing this down in words, why don't I write it down symbolically? All right, so properties. Vector A plus B is the same as vector B plus A because you're just adding per component. Vector addition is also associative, meaning it doesn't matter how you group. In the end, you'll get the same result. And then finally, the zero vector is there so that we have an additive identity. When added to any vector A, it's still going to be the same vector A. And then when you add to the vector A, the vector which is the negative of that vector, what we get is the zero vector. You can think of that in terms of the components. The corresponding components are just going to cancel each other. But also because when you think of traveling along vector A, following up with travel along vector negative A, you're just reversing and same distance. So that means you're going to end up precisely where you started. And then you have the usual distributive properties. So C times vector A plus B, no different from CA plus CB. Diyan baba. C plus D times vector A, the same as CA plus DA. All right. And then scalar multiplication, let's say CD multiplied to A. It's no different from, let's say, multiplying the scalar D to A first and then afterwards to C, or multiplying the scalar C to A first and then afterwards to D. And then some of the most difficult to remember properties, the scalar 1 times the vector A is the vector A. Right? Very difficult to remember, don't you think?
It's a super hard property po. Why does it exist?
Oo nga eh, ang hirap. Ano? Okay. So other properties, one of which I have already written down already. The length of a vector is zero if and only if it's the zero vector. And then if C is a scalar and you multiply it to the vector A, then this is equal to, so the length of this new vector is it C times the length of vector A?
I think po.
Is that
Ano? Yes. Scalar lang kasi.
scalar lang? But hey, C can be negative, right?
Opo.
Di problema yun kasi nung left side non-negative. That's nung right side. What if C is negative? Dapat this should be Absolute value of C.
Value rin.
Oo.
Isn't that literally parang normal po?
What do you mean parang normal?
Parang normal absolute value multiplication.
I get what you're saying. Parang ganon. But strictly speaking, no. Because when you look at C versus this, even though you're using the same two symbols, you're using the same pair of vertical bars, they are actually used differently because you're applying them on different objects. We just happen to be using the same symbols. So in the first, that's absolute value. In the second, it's the length of a vector for which you have to take a square root. Okay. Ano pang properties we have? So we have above the algebraic properties, and then this second set. These are the geometric properties. The triangle inequality. The length of the sum of the two vectors A and B is less than or equal to the length of vector A plus the length of vector B. So observe that we have less than or equal to, because it's possible for equality to occur. And in fact, equality occurs if and only if kailan kaya yun mangyayari for equality to occur. Okay, well, let's say this is vector A, and this is vector B. And let me use a different color. This is vector B. Now the location is irrelevant, so I could draw vector B like so. And as for vector A plus B, it's going to be this, starting from A, going to B. But we have just pointed out vector addition is commutative, so A plus B is the same as B plus A. Okay, A plus B is the trip around above the diagonal. B plus A is the trip below the diagonal. But we see that, hey, it's the same. So in fact, if you draw A and B starting from the same point and you complete this parallelogram, A plus B is that diagonal starting from where A and B started towards the opposite endpoint. So that is vector A plus B. Now, if you look at the triangle that's formed here, because yeah, that's what's gonna happen. You get a triangle whose sides are the lengths of the vectors. So here, the length, how long is this side? The length of vector B. And then how long is this side? The length of vector A. And then how long is this other side? The length is going to be the length of the sum of the two vectors. And from the triangle inequality, in this case, we have a non-degenerate triangle. We then see that the length of A plus B is strictly less than the length of A plus the length of B. Now, in this illustration, I drew A and B so that the vectors are not parallel. But what would happen if they were parallel? Now, if they were going in the same direction, okay, so this is vector A, and then vector B is this. And then if you draw vector A plus B, it would be this. And so in this case, because A and B are going in the same direction, then we see that yes, indeed, the length of the sum is equal to the sum of the lengths. Okay. All right. But what if A and B are going in opposite directions? So let's say this is vector A, and then if we draw vector B, immediately after the tip of vector A, so let's say this, oops, this is vector B. Okay, where then is the sum vector? It's from where A started going to where B ends. So this is A,
Still the same concept po.
ayan.
Yeah, still the same concept po, where A started to where B ends.
So ayun, so nung A plus B, the blue vector, and with the correct arrowhead. And then in this case, we see that the length of A plus B is in fact strictly less than the length of A plus the length of B. In fact, from the illustration, we see that the length of A plus B, the blue vector, is strictly less than the length of the orange vector, the vector B. So from the triangle inequality, we see that equality occurs if and only if A and B are going in the same direction.
Opo.
Have the same direction. So it's not enough that they're parallel because we see that, okay, if they're parallel but in opposite directions, then the inequality is going to be strict. Okay, let's talk about one other operation. And I think you already have some familiarity with this, the dot product.
Opo.
Have you okay? When did you encounter the dot product
In ano po, sa physics po.
as a physics? All right, sa physics. So, saan yung ginagamit ng dot product sa physics?
Sa ano po, kasi ginagamit po sa ano yung motion about something po biglang. Iniisip ko po, ayun, yung sa, ano po, yung for work.
Okay, yeah, for work. Okay, work.
Force and
Yeah.
displacement po
Force dot displacement.
Opo.
Okay. So actually, pwede natin i-tie up doon sa discussion natin. Then force dot displacement. So okay, A dot B. So we can take the dot product of two vectors having the same number of components. So ito, I'm going general and components. This is A1, B1 plus A2, B2 plus dot 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 plus A sub n, B sub n. So observe that A dot B is a scalar rather than a vector. We had scalar multiplication earlier, but it was between two different objects, a scalar times a vector. This time we are multiplying two vectors. However, this is not the only multiplication possible. And so that's why when we want to talk about the dot product, we have to use the dot symbol. All right. We see here that dot multiplication is commutative. Is it associative?
Tingnan po natin. Kung A, B, C, AB1, AB2.
Commutative, which means A dot B equals B dot A.
Hindi po siya associative kasi
Okay, you're right.
Opo.
Alright. So kasi, about you have three vectors and they all have the same number of components. If we look at A dot B and then dot C, and if the question is, hey, is this the same as A dot B dot C? What would be your explanation?
Bakit hindi po sila associative? Because if A and B are scalar, tapos and C is vector, they have no dot product.
And I mean, A and B, vectors sila. A, B, and C are all vectors. But if you look at A dot B, is A dot B a vector?
No, yun nga po. So A dot B,
Yeah, okay. I thought you know.
dot product with there's no dot product po between the scalar and vector.
All right. Okay.
Scalar po,
Dot
hindi po
is only between vectors. All right. So associativity is not even going to be supposed to be an issue. All right. Now let's have a look at some of the quick properties of dot products. So you've seen dot products before. Do I need to give an example or hindi na?
Hindi na po.
All right. So properties. So number one, A dot B equals B dot A. And then ito, A dot B plus C. So we have the distributive property. A dot B plus A dot C. And then hey, what about ito? The zero vector dot A.
Oh,
Kaya mo yan, kaya mo yan.
zero po.
All right, okay, zero. Okay, and same with scalar multiplication. Halimbawa, we're looking at C and then A dot B. Okay, C is a scalar because there's no arrowhead above it. So that means hindi kailangan ng dot after C. So this can be taken as
So pag
CA.
nag-vector po, you cannot use, you must only use parentheses to denote multiplication.
Ano yan? If so actually ganito because it's actually there's not going to be any confusion if you write down C A dot B because the many different interpretations, either this or this, they're going to be the same anyway. So which means when you see something like that, there is not supposed to be any confusion. You can take it like this or this because of this property.
Opo.
Pwede pa natin ilagay A dot C B. Wala pa tayong mga pinuprove. Gusto ko magbigay ng geometric properties, but we are on our way there. One other property, what happens when you take the dot product of a vector with itself?
Squared.
All right, let's say A is A1, A2, all the way to AN. So when you take the dot product of vector A with itself, diba, you multiply the corresponding first components, and it's A1 for both, so it's A1 squared, and then A2 squared, plus dot dot dot, plus A sub n squared. Observe that, hey, what we have here is the sum of the squares of the components of the vector A. And you might recall that we already used up the sum of the squares of the components here. Oops. They see this.
Opo.
So the sum of the squares of the components appears in the square root defining the length of the vector, which means if you square both sides, then the square root will disappear. It will just be the sum of the squares of the components. In other words, this thing that we're writing down here is the square of the length of vector A. So in other words, the dot product of a vector with itself is a non-negative number because it's the square of the length of that vector.
No.
So when is the only time the dot product of a vector with itself is going to be 0?
When the vector of y sub is the zero vector?
All right, yeah. Can the dot product be negative?
No. Kasi po lahat all of them are positive. There's no, wait, yes.
Yes, yes, yes.
Lahat sila negative.
So pwedeng negative. So the dot product can be any number. Right? Pwedeng positive, pwedeng 0, pwedeng negative. But when you take the dot product of a vector with itself, it's going to be a non-negative number because it's a square of the length of that vector. Now we're getting closer to geometry. Well, one particular reason why the dot product is very useful as far as the geometry of vectors is concerned. Okay, let me draw vector u and vector v, starting from the same point. Now there are two angles, this and the other one. Both of them, when taken together, add up to 360 degrees. Now, there are many instances where it is useful to take note of the angle between two vectors. But in deciding which of the two it is, by definition, the vector between the two angles is the one I marked by theta because it's less than or equal to 180 degrees. The angle theta between vectors u and v is the angle theta in the illustration where theta is greater than or equal to 0 degrees and less than or equal to 180 degrees. Okay. What's the situation when the angle between two vectors is 0 degrees?
Then, yung ano po, yung kanina po, parang horizontal po sila.
And in fact, they're pointing opposite or same direction?
Same direction po.
Same direction. What about the other extreme when theta is 180 degrees?
Yung isa po, they're pointing in opposite directions. The shorter one will be the magnitude that the larger one has been decreased.
All right. Okay. So, well, or you're just parang thinking of drawing the two vectors starting from the same point. So yes, you're going to be pointing in opposite directions. So that means if two vectors are parallel, then the angle between them is either 0 degrees or 180 degrees. For any of the other angles, strictly between 0 degrees and 180 degrees, the two vectors are not parallel. All right. Theorem. If theta, okay, if A and B are non-zero and theta is the angle between them, then A dot B equals the following. The product of their lengths multiplied by the cosine of the angle between them. So A dot B equals the product of the lengths of vectors A and B multiplied by the cosine of the angle between them. So let us prove this. We're gonna prove this. Well, first let's get rid of some pesky situations. In particular, when theta is 0 and when theta is 180 degrees. Okay, first, okay, suppose theta is equal to 0 degrees or 180 degrees. Then that means A and B are parallel. Diba? We already talked about this earlier. A and B are parallel. If theta is 0, they're pointing in the same direction. If theta is 180 degrees, they are pointing in opposite directions. But if two vectors are parallel, I realized I wasn't able to emphasize this earlier, pero ganito. Okay, yeah, actually, it was when we were talking about ito. If you look at uh, this collection of vectors, u, 2u, negative u, negative 1/2 u. These vectors are all parallel, right? And actually, the reason why they're all parallel is because they are scalar multiples of each other.
Opo. Isa po
Okay.
ang negative is may iba po. May iba.
So actually, that's a characterization of parallel vectors. If two vectors are parallel, then that means they are scalar multiples of each other. So in this case, if we're assuming A and B are parallel, thus we can write down vector B as k times the vector A for some number k. Pwede rin naman A is kunwari, S times vector B. So basta one is, kasi after all, diba, if A is twice B, you could also write that down as B is half of the vector A. All right, so it doesn't matter which one you write as a multiple of the other. Okay, then let's have a look at the left side. In this case, A dot B will be A and dot K A. But then K is a scalar, so this is K, and then A dot A. And then A dot A is the square of the length of vector A. Then let's not forget K. All right, now, so ito nung left-hand side. We're proving that the left-hand side equals the right-hand side under the situation where A and B are parallel. Mamaya na if A and B are not parallel. For now, let's just take care of this situation. All right, now let's have a look at the right-hand side. For the right-hand side, though, that involves theta. So we're going to have to look at the two scenarios. Let's say theta is equal to 0 degrees. So not only are A and B parallel, they are going in the same direction. A and B have the same direction. But if they have the same direction, then that means the scalar multiple that was multiplied to A must be positive. K is positive. So now let's see, what would the right-hand side produce? Length of A, length of B, and then cosine of theta, length of A. And then B, let's replace it by KA. And then cosine of 0 degrees. Now, the second factor you have vector A there, but then you can take out the scalar k as it is because k is positive. You don't need the absolute value of k because k is positive anyway. And what is cosine of 0 degrees? That's 1. So we end up with k, and then the length of A times the length of A. So the square of the length of A, and observe that this is the same as, so we started with the right-hand side. This ends up being the same as the left-hand side. What if theta is 180 degrees? So that means A and B have opposite directions. So if A and B have opposite directions, what's our conclusion?
They cancel each other. Negatives of each other.
Well, if they have the same length.
They have the same length po. Pero yung ano nila yung...
So what if you have A and then negative 2A? Diba? But the point is, where earlier, if theta is 0 degrees, so A and B are in the same direction, that means the scalar factor is positive. But then, diba, if you want to reverse the direction of a vector, you multiply it by a scalar which is negative. Thus, k is negative. All right, so let's have a look at the right-hand side. Length of A, length of B, and then cosine theta, length of A, and then, well, still length of KA, but then cosine 180 degrees. Now, cosine of 180 degrees is -1. Now, so length of A, and then it's the absolute value of K. But because K is negative, then that means the absolute value of K is -K. And so now what? We have length of A, -K, length of A, -1, but -K and -1 end up being just K. And then we have the square of the length of A, which is the left-hand side. All right, so that means the identity is true, and we've justified it when the two vectors A and B are parallel. And we've covered both the cases where they're in the same direction or opposite directions. So now, ito na talaga ng meat of the proof. Suppose A and B are not parallel. Now, if they're not parallel, then that means when you draw vectors A and B, you actually get to form a non-degenerate triangle. A and then vector B, and then actually, ano ba ang gusto kong buuin? I want to form, I want to draw the sum. Wait, is it the sum ba? Or actually, ganito. I already have a triangle here. Ito, Joshua. This green vector, okay, that arrowhead. What is that? Is that A plus B or A minus B or B minus A?
B minus A.
Correct. B minus A. But hey, what we get is a non-degenerate triangle, and angle theta is here. Theta is opposite the green side. Now, what we're going to do is come up with an equation which involves the included angle between those two orange segments. There is a trigonometric law that we could use here. It's the law of
Cosine.
law of cosines. From the cosine law, the length of the green vector, so that's B minus A and then squared equals the sum of the squares of the other two sides. But that would be the square of vector A plus the square of vector B minus twice the product of the lengths of the two orange sides, length of A, length of B, times the cosine of the angle theta. We're going to use here more than once what we already established earlier. Recall that the square of the length of a vector v is nothing more but its dot product with itself. So that's going to allow us to rewrite the left side as follows. B minus A dot B minus A. And then on the right side, A dot A plus B dot B minus, well, nothing much we can do with this for now, just the product of the lengths of A and B and then cosine theta. Now, remember earlier we listed down the algebraic properties of the dot product. So if you look at, for example, the one that I just checked, what that's showing us is that we have the distributive property. Now, when we do multiplication of polynomials, for example, when you do x times x plus 2 and you write it down simply as x squared plus 2x, what we're really employing here is the distributive property. In other words, even if the operation is not ordinary multiplication between real numbers, but this time dot multiplication between vectors, we can still proceed as if we were multiplying polynomials. So you can do B dot B and then B dot negative A, which you can write as minus A dot B because dot multiplication is commutative, another minus A dot B. And finally, minus A dot minus A, two negatives make a plus A dot A. A dot A plus B dot B minus twice the length of A, the length of B, and then cosine theta, and then we see that a lot of these things are going to kill each other. B dot B, A dot A. On the left side, we have negative twice A dot B equals negative twice product of the lengths times cosine of theta. And a straightforward cancellation by -2 gives us the following remarkable fact about the dot product, that it is the product of the lengths of the two vectors times the cosine of the angle theta between them. All right. So here's an example. There. Oh. Wala na pa si Sir. Sulat. All right. Uh, Iba na lang. Kasi itong problem that I was thinking of, pwede siyang isolve without using the dot product. A, and then 2, -1, 0, and then B, 5, -4, 3, and then C is 1, -3, 2. Find angle A in degrees to 2 decimal places. So observe that if we are to draw uh, the triangle, this is going to be in three-dimensional space. And so using what we know about, um, using what we know, well, parang hindi straightforward hanapin nung angle. Well, actually, pwedeng gamitin ng trigonometry because, well, the cosine law still applies. If you want to find angle A, then we need the lengths of the three sides. Actually, that's one option. You could use the cosine law. But alternatively, we can use the theorem. Kasi ganito, schematically, you have A here, and then B not drawn to scale, but we don't need it drawn to scale anyway. C. And then this is angle alpha. And then angle alpha is the included angle between vectors AB and AC. But the thing about vectors AB and AC is that coming up with their components is as easy as just performing subtraction on the components. All right, so let's have a look at AB. Ano components ng AB?
3, 5, ano, yeah, wait. 3, -1, -4, -3, tapos 3.
What about AC?
1, -1, -2.
Again, ano first component na?
-1.
-1, -1, -2, and
2 po.
2. Okay, what are the lengths? For 3, well, we can observe that 3 is 3 times 1, -1, 1. Ibig sabihin, AB is 3 times the length of 1, -1, 1. So 1 squared plus 1 squared plus 1 squared. Of course, pwede namang i-mental 3 squared of 3. What about the length of AC? Three, exactly 3. And from what we just proved, the dot product AB dot AC, okay, is equal to the product of the lengths times the cosine of the angle alpha between AB and AC. The product of the lengths, that's 3 square root of 3 times 3, and then cosine alpha. I use the dot, but it's clear it's not dot product because it's just real numbers. Now, as for AB dot AC, we just multiply corresponding components. 3 times -1, -3, plus 6, plus 6. So on this side, that's 9. Which means if you solve for cosine alpha, that's going to be 1 over the square root of 3. Did I do that right? 1 over the square root of 3. Tama, no? All right. And so that means alpha is cosine inverse of 1 over the square root of 3. Well, you know how, for example, if you look at the equation cosine x equals 1 half, this has infinitely many solutions. However, in this case, when you look at cosine alpha equals 1 over square root of 3, fortunately, between 0 degrees and 180 degrees lang yan. So that means the solution is unique. So as soon as you find cosine inverse of 1 over square root of 3, if I'm not mistaken, that's 54.74 degrees, then that's it.
Bro.
All right. Okay, so it's 8:32. There's a lot more to do. Nasa dot product pa lang tayo.
Kapag umabot pa ng cross product, masasira na po yung ulo ko.
Okay. Medyo mabilis din ng ginawa natin. Pero, well, at least there's already some familiarity with the dot product. Okay, but I feel like maybe some things kasi were not presented this way. And we're seeing, hey, is it your first time to see this property? A dot B and the angle between them. This theorem.
Yung, alam ko po without the, di kasi sa akin po yung pagka-magnitude po, simply A o kaya B.
No, I mean, this fact, have you seen this before?
Yung equivalent niya po, yes po. Pero yung,
okay.
in this way, hindi po.
In this notation, hindi pa. All right. Anyway, sige, we are gonna continue this next time. All right?
Thank you po,
Thank you po.
sir.
Sige, pahinga ka na ano ba? Parang nagtuloy-tuloy ka yata kasi, all right, so time to rest. Okay, Joshua, thanks for being a trooper. Sir Jay, bye-bye.
Thank you po.
Thank you po. Bye-bye po.